Have you ever wondered what light is really made of? Or what about an electron, one of the tiniest things we know of? You might think of them as very, very small balls, like tiny marbles zipping through space. And sometimes, that is exactly how they act. But what if I told you that sometimes, these same tiny things can also act like waves in the ocean? How can something be a solid little particle and a spread-out wave at the very same time? This isn't a riddle. It is one of the biggest, most mind-bending questions in all of science, and it led scientists to a completely new way of understanding our universe. This idea is called wave-particle duality. It sounds complicated, but it just means that some things in our world have two different personalities. Think about it like this. You can be a student in a classroom, but you can also be a player on a soccer field. You are still you, but you act differently depending on where you are and what you are doing. In the weird world of the very small, things like light and electrons have this dual nature. They can behave like a particle, a single dot hitting a target, or they can behave like a wave, spreading out and interfering with itself. This strange fact is not just a cool idea. It is something we can see in experiments. The journey to understanding this started a long time ago. For centuries, scientists argued about light. Some, like Isaac Newton, thought light was made of tiny particles he called corpuscles. Others thought light was a wave, like the ripples you see in a pond. For a while, the wave idea seemed to win, because it explained a lot of things really well, like how light can bend and spread out. But then, new experiments came along that showed light acting like a particle again. It was a huge puzzle that did not seem to make any sense at all. How could both sides be right? This was not just some small detail. It was a crack in the very foundation of what we call classical physics, the rules for baseballs and planets. So, how do we know that light can act like a wave? We can show it with a famous and amazing experiment called the double slit experiment. Imagine you have a wall with two thin slits cut into it. The slits are parallel and side by side. Now, on one side of the wall, you shine a light. On the other side, you place a screen. The screen is like a movie screen that will show you where the light lands. If light were just a stream of tiny particles, like little paintballs, you would expect to see two bright lines on the screen, right behind each slit. That seems like common sense, does not it? But that is not what happens. When you shine a light beam through the two slits, you get a surprising pattern on the screen. Instead of just two bright lines, you see a whole series of bright bands and dark bands, all spread out. The brightest band is in the very middle, right between where the two slits are. This pattern of light and dark stripes is called an interference pattern. It is the same kind of pattern you get when two waves in a pond meet each other. Where the peaks of the waves add up, you get a bigger wave, a bright band. Where a peak and a trough cancel each other out, you get nothing, a dark band. This interference pattern is the classic signature of a wave. It proves that light is behaving like a wave when it goes through the slits. Each light wave seems to go through both slits at the same time, creating two new waves on the other side. These two new waves then spread out and interfere with each other before they hit the screen, creating that distinct striped pattern. It is as if each single bit of light somehow knew about both paths and traveled them simultaneously. This result was a huge victory for the Light as a Wave team for a very long time. Now for the really weird part. Scientists decided to try the same experiment with electrons. Electrons are definitely particles, right? They have mass and a charge. They are tiny bits of matter. So if you shoot electrons one by one at the double slits, you should definitely get two lines on the screen behind the slits, just like our paintball example. At first, it seems to work that way. When the first electron hits the screen, it makes a single dot. The next one makes another dot, and another. They are clearly arriving as individual particles. But if you wait long enough and let thousands of electrons hit the screen, something incredible happens. They act like particles when detected, hitting as dots, but like waves as they travel, creating the interference. They have both identities at once. Scientists were baffled. They decided to find which slit each electron went through. So they put a tiny detector camera beside the slits. If we can see which slit it went through, we can solve the mystery. But when the detector was turned on, the interference pattern vanished. With the detector on, electrons behaved like particles again. The screen showed two bright bands behind each slit, like paintballs. Observing the path forced the electron to choose a single path. When you were not looking, it acted like a wave through both slits. When you looked, it acted like a particle through one. This discovery is profound. At the quantum level, the observer is part of the experiment. How you measure changes the outcome. It is not just clumsy detectors, it is a fundamental property of nature. The universe will not show wave and particle at the same time. You can ask, "Are you a particle?" It says yes. Ask, "Are you a wave?" It says yes. But you cannot ask both at once. While the double-slit experiment was revealing the wave-like nature of particles, another experiment was busy showing the particle-like nature of light. This was called the photoelectric effect. Here's the idea. When you shine a light on a piece of metal, sometimes it can knock electrons loose from the metal's surface. Scientists noticed something strange though. It was not the brightness of the light that mattered for knocking electrons off. You could shine a dim blue light, and electrons would pop off instantly. But if you used a very, very bright red light, nothing would happen, no matter how bright it was. This did not make sense if light was just a wave. A brighter, more intense wave should have more energy, so a bright red light should have been much better at knocking electrons loose than a dim blue light. It was Albert Einstein who solved this puzzle in 1905. He proposed that light is not a continuous wave after all. Instead, he said light travels in little energy packets, like tiny bullets. He called these packets quanta of light. Today, we call them photons. According to Einstein, the energy of each photon depends only on its color, or its frequency, not on the brightness of the light. Blue light is made of high-energy photons. Red light is made of low-energy photons. Brightness is just the number of photons. To knock an electron out of the metal, a single photon needs to have enough energy to do the job. A blue light photon has that energy. A red light photon does not. Even billions of them cannot free an electron. It is like trying to knock down a bowling pin with ping-pong balls. This brilliant explanation of the photoelectric effect showed, without a doubt, that light acts like a particle. So now physics had a huge problem. The double-slit experiment proved light is a wave. The photoelectric effect proved light is a particle. Both experiments were correct. This meant light was somehow both. This led a young French physicist named Louis de Broglie to have an even bolder thought. If waves like light can act like particles, then maybe particles like electrons can act like waves. He proposed that anything that has momentum, anything that is moving, also has a wavelength. Louis de Broglie came up with a simple but powerful formula. He said the wavelength of any object equals Planck's constant divided by its momentum. Planck's constant, a tiny fundamental number. Momentum, that is mass times velocity. For big things, a baseball. For big things, a person walking down the street. Their wavelength is unbelievably tiny, too small to measure, so we do not see people acting like waves or making interference patterns walking through two doorways. Our everyday world is just too big for these quantum effects to be noticeable. But for a very, very small particle like an electron, the story changes. An electron's tiny mass means a much larger wavelength, big enough to detect. De Broglie's idea was theory at first. A few years later, an experiment proved him right. Electrons made clear wave interference patterns, matching de Broglie's prediction. Wave-particle duality was not just for light, it applied to all matter. These discoveries changed how we see reality. The world is not just solid little balls, nor just smooth waves. At the fundamental level, it is strange quantum entities that are both. Quantum mechanics gave us the rules for this tiny, weird world. It led to lasers. It led to computers. It led to medical imaging like MRI. All of these work because we understand electrons and photons' quantum behavior. Our modern world is built on this strange science. Next time you look around, remember beneath our predictable reality, there is a buzzing quantum world science still seeks to fully understand. Things can be in multiple places at once. The act of looking can change something. Particles can be waves. Waves can be particles. The double-slit experiment did not just change physics. It opened our eyes to the deep, beautiful mystery of the universe. That is why science is amazing. There is always another surprise. We are all made of atoms. Atoms are made of quantum particles. We are all made of wave particles. Wow.